Hi guys, I'm Tush, and today I'll be talking about Einstein's coefficients, and I will explain how the coefficients are related to each other, so their relationship, and what kind of conclusion you can draw from their relationship. To understand this, first of all, you have to understand three processes by which radiation interacts with matter. So, before I jump into explaining the three processes, I have to first explain a little bit of the history behind this. So, in 1917, Einstein introduced the model of interaction of radiation and matter. He basically considered two levels of an atom, so an upper level associated with the energy E2 and a lower level associated with the energy E1. Okay, and I'll explain this a bit more when I explain the three processes. So he established three processes by which radiation, electromagnetic radiation, could interact with atoms in these levels. So the three processes are, as you can see, I've written over here, absorption, spontaneous emission, and stimulated emission. So in absorption, as you can see, the two levels. The first level is ground state level, which is E1, and the second level is the upper state. So, the upper level, that's E2. And over here, you can see I've written here N2 and N1. Some of you might already know this. This is the number density of atoms in the lower level and upper level. So you have to first understand the levels, I guess. So first of all, I just put it in my head as the lower level with energy E1, number density N1, and the upper level with number density N2 and energy E2. So that's in all three processes, you just have to keep that in mind, that the second one is 2, 2 basically, both N and E. So absorption, what it is, basically, electromagnetic radiation comes in, h nu, which is the energy of a photon. So radiation, tiny packets of energy. That energy is Planck's constant, and nu, which is the frequency. So you can see that this is based on Planck's radiation law. So so photon comes in, it's absorbed, and the atom jumps to the upper level. That's basically what it is. Very simple. Radiation, atom jumps to the upper level from the lower level. Second one is spontaneous emission, which is basically that it's spontaneously, it's not induced, nothing triggers it, it's just spontaneously. That's what it's called, spontaneous emission. Spontaneously, atom jumps from upper level to lower level, and that causes a photon to be emitted. That's why we have this emission over here, the photon emission. So very simple, I'll just go over it again. So atom spontaneously from upper level jumps to the lower level, and a photon is released. The third one is stimulated emission. So you have atom here is made to jump to the lower level, and two photons are released. So this is not spontaneous. Okay, this is like we trigger it so that two photons are released. So these are the three processes. You have to keep in mind the differences between these three processes. And you have to keep in mind E1, E2 are the energy levels. And radiation over here, this is photon coming in, h nu Planck's constant, and nu, which is the frequency, not v, not velocity, it's the letter nu, and it's the frequency. N1 and N2 are the number densities of atoms in upper and lower levels. So now I will basically move on to explaining the mathematical relationship between these, which includes a bit of maths and calculation. So let's go and check that out. So let's first look at absorption. So as I said before, in absorption, photon comes in, so radiation comes in, photon gets absorbed by the atom in the lower level, and the atom jumps to the upper level, where the number density of atom is denoted by N2 and the energy is E2. So first of all, what we have to know is that the energy of the photon is Planck's constant times Greek letter nu, which is a frequency, which equals the upper level, energy of the upper level, take away the energy of the lower level. So that's what we want to know, okay? So you have to keep that in mind. And the second point is that E as a function of nu is the energy density of incident radiation. So you know these two things, great. The next thing, what we're looking at is the rate of absorption. So we're actually looking at the rate of spontaneous emission as well, and the rate of stimulated emission. So what we're doing is first looking at the factors that basically contribute to the rate of absorption and spontaneous emission. So what I mean by that is we'll see that the rate of absorption, RA, depends on, so I'm showing that with the directly proportional sign, depends on the number density of atoms in the lower level, so N1. And it also depends on the energy density of incident radiation, so E nu. Okay, so we can say that obviously the overall factor is that rate of absorption is directly proportional to N1 and E nu. So now we have here a directly proportional sign. So if we were to equal it, then we would need a constant of proportionality in front of N1 and E nu. So I'll just write that down over here, make some space. Okay, now, okay, so we've written here is directly proportional to N1 E nu. So if there was an equal sign, so over here I'm just keeping it blank, there would be a constant of proportionality, right? That's how I try to remember it. So you would need some sort of coefficient here. So this coefficient is basically the Einstein coefficient for absorption, which is B. Actually, I'll write that down with some other color. So that is basically B 2,1. So it's 2,1 because the atom is jumping from the lower level, so level 1, right, to level 2. So you can remember it that way, that the coefficient for absorption, because it jumps from level 1 to level 2, it's 1, 2. So B1, 2. So basically, you can say the rate of absorption equals Einstein's coefficient B12 N1, which is the number density of atoms in the lower level, times energy density of incident radiation. Okay, so that's all we need to know, that equation. Okay, but you know now how we reach that equation. So the next one is spontaneous emission. So the rate of spontaneous emission depends on, basically, I'll show you over here. I just got a different colored pen. I'll say SE depends on the number density of the upper level. Very simple. I guess it kind of makes sense because you don't have any photon coming in here to trigger it. It's just a spontaneous emission. So it seems to be depending on the upper level, which is the N2 number density of atoms over here. So it only depends on the number density of upper level. So it spontaneously jumps from the upper level to the lower level, and that causes a photon to be released. Right, so the rate of spontaneous emission, so the rate at which this spontaneous emission occurs, is directly proportional to N2, the number density of the upper level. So now again, I'll explain that this is a directly proportional sign. So if we were to change it to equal, we would need here a constant of proportionality, so N2. So that constant is again the Einstein's coefficient. So for Einstein's coefficient, the we write here A. Actually, that's not a nice A. I'll write it better. A 2 1. So now it's 2 1 because the atom is jumping from upper level, which is 2, so the second level, to the lower level. So we can write the final equation as that the rate of spontaneous emission, okay, SE equals Einstein's coefficient A to 1 and times N2. Okay, that's simple, very simple. And then next we got stimulated emission. Over here we see that a photon comes in, triggers the atom. So we stimulate the atom to jump from the upper level to the lower level. We stimulate it by with the help of this photon coming in. Okay, so the photon comes in over here, and the atom jumps from the upper level to the lower level. This causes 2 photons to be released. Okay, so the rate of stimulated emission, oops, I'll just do it back to purple. Rate of, just do that with SD, emission, stimulated emission is directly proportional, so depends on N2. I think this is again making sense because the initially it's at N2 and it's jumping from N2 to N1. So it makes sense that the rate of stimulated emission is depending on the upper level number density of atoms. So it depends on that. So that's why we're using a directly proportional sign here again. And it also depends on the energy density of incident radiation, like absorption over here. I've written it over here. So that means the overall factors are both that influence the rate of stimulated emission are both N2 and the energy density of incident radiation, right? So I'll just write that down as STE directly proportional to N2 and E nu. So again, if we were to change this sign into equal, we would need a constant of proportionality. And that constant of proportionality is Einstein's coefficient. So the coefficient we are going to put over here is B 2, 1. I know it's the same as the absorption coefficient over here, but the only difference is it's from the upper level, so 2, jumping to lower level 1, so it's B2, 1, whereas over here it's 1, 2. So you can think of these two processes as kind of being opposite, right? Because this photon coming in and triggering the atom to jump from lower level to upper level, so 1, 2, B1, 2. And over here, this photon is triggering the stimulating, that's where stimulated. So stimulating the atom to jump from upper level to lower level. And as I said, it causes 2 photons to be released. So these are our final equations, right? Over here, this one. So it's a bit messy, but I think you get the point. Over here, this one. And this one. So now we will look at how they're related. We just needed these 3 basic equations. So the rate of absorption equation, the rate of spontaneous emission, and the rate of stimulated emission. So as you can see, I've written the 3 equations over here: rate of absorption, rate of spontaneous emission. So over here, as you can see, I've written dN1 divided by dt for all 3 equations, because this is the change in number density of atoms in state 1, so level 1 over here, per unit time, which is basically the rate of the processes. And next, we're going to see that in thermal equilibrium, this change in number density of atoms per unit time is equal to 0, because N2 and N1 are both constant. So, and when that is the situation, we see that absorption equals spontaneous emission plus stimulated emission. And I've plugged in these equations for absorption. So rate of absorption is B1, 2, and 1 E nu. So I've plugged it in over here. So this is over here. Rate of spontaneous emission, A2, 1, and 2, goes over here. And rate of stimulated emission, plugged in here. Now, as you can see, I have taken this bit of the equation, stimulated emission, on the left-hand side of the equation. When I do that, the plus sign changes to minus. And spontaneous emission, A2, 1, and 2, remains on the right-hand side. Now, over here, as you can see, I've taken E nu common out. So I've taken this bit out from this side of the equation over here. And I am left with B2, B1, 2, and 1. Take away B2, 1, and 2, which equals A2, 1, and 2. If I take this bracket down on the right-hand side of the equation, then this is what we get. A2, 1, N2 divided by B1, 2, N1, take away B2, 1, and 2. And then if I take B2, 1, N2 common out from the denominator of the equation, you can see that inside this bracket, I am left with B12N1 divided by B21N2, take away 1, because these two will cancel out. And if I times B21N2, take away 1, if I times these two things, then I'm left with B minus B21N2. So basically, if I take this common out, I'll be left with this inside the bracket. Now I can cancel N2 over here and N2 over here, and then I'll be left with E nu equals A21 times 1 divided by B21 times B12N1 divided by B21N2, take away 1. According to Maxwell-Boltzmann's distribution law, you can see that N1 divided by N2 equals e to the power of energy in the upper level, take away energy in the lower level, divided by Boltzmann constant times absolute temperature. This difference in the energy level is equal to the energy of the photon, which is h nu. Now if I plug in N1 divided by N2 over here, so I'll just erase that. Then I will get the following. E to the power of h nu divided by k b t, take away 1. And we know that E nu equals 8 pi Planck times Planck's constant nu to the power of 3 divided by c to the power of 3. So I'll just write that down over here. I just have to make some space. I hope you guys have written this bit down. Okay, so we know that Planck's radiation law is nu 8 pi Planck's constant nu to the power of 3 c, that's speed of light, is e to the power of k b t, take away 1. Right. So we can compare now that this bit, A21 divided by B21, is same as this. The fraction over here, 8 pi Planck's constant nu to the power of 3, c to the power of 3. Sometimes you will see it as 2 Planck's constant nu to the power of 3 divided by c to the power of 2. That's correct as well. There's different forms of Planck's radiation law. There's 3 forms, I think. This is because of the radiometric quantities. But if you see this, that's correct as well. I'm just using this in this video. So I'll just erase that for now. So now I can see that A21 divided by B21 is basically this, if we compare these two equations, this one and this one. So I can write A21 divided by B21 equals 8 pi Planck's constant nu c to the power of 3. And I can write that I'll just write it, and B12 divided by B21 equals 1, because in front of this we have nothing, so it's like times 1, which is the same as here, B12 divided by B21. Okay, and if we make B12 the subject, then we see that B12 equals B21. So we found out that A21 divided by B21 equals 8 pi Planck's constant nu to the power of 3 divided by c to the power of 3. So the first conclusion that we can draw from this is that the ratio of spontaneous emission and stimulated emission depends strongly on the photon energy, as you can see over here. And conclusion number 2 is that the probability of absorption and stimulated emission are equal over here.